nanohub.org. Online simulation and more for nanotechnology.
Our speaker today is Joseph Kern from Georgia Tech. So Joe is a material science and engineering graduate student at Georgia Institute of Technology in the Rampi Ramprasad group. Prior to grad school, he dual majored in material science and computer science at University of Wisconsin-Madison. He also spent 6 years in the Minnesota National Guard as an Arabic linguist, which is something that we don't typically see with our workshop presenters. So, thank you for that interesting, piece of information, Joe. Very impressive. His research involves utilizing computational techniques such as genetic algorithms and machine learning to expedite materials discovery in the polymer chemical space.
Okay, yeah. So like Arun said, I am Joe. I am a PhD student at Georgia Tech in the Ramprasad research group. So I'm going to talk about genetic algorithms and integrating those with machine learning to actually create new hypothetical polymers. Just want to shout out to a paper we wrote recently. At the bottom, you can see the reference to it there. And thank Lihua Chen and Chiho Kim and Dr. Ramprasad for helping with this research. So I'm going to quickly talk about what genetic algorithms are, go into what PolyGA is. And then I'm going to talk about how you would make a genetic algorithm if you wanted to. This is going to be about polymers. I understand a lot of you probably aren't doing research in polymers, so I'm trying to make it as general as possible. And then I'll go into what fitness functions are and how to run PolyGA. So to start, I'm going to go over this beautiful graphic I made by hand. You can tell I made it by hand because of how beautiful it is. So this is what a genetic algorithm really is. It's about taking in the environment some sort of environmental factor that can positively or negatively influence the fitness of a material or in real life an animal. So in this case, we have some polar bears. Because of global warming, they're all dying. Very sad and true. So only brown bears actually move on to the next generation. They have some mating that occurs, some crossover. And after that, a crossing over of their kids or of their genes, they have some children. These children have slight mutations that might occur. And then in that scenario, maybe you have a little black bear that gets born. Maybe it's a little smaller than a brown bear. And at the next generation, we're going to see if the features of this new child are beneficial towards surviving in the future. So maybe because it's smaller, it's able to release heat better, so it can survive in this higher temperature environment, but it's also black. So maybe it's not going to actually survive as well because it absorbs more heat. So I understand in real life, black bears aren't made from brown bears, but bear with me here on this analogy. So in terms of materials design, we use it to solve the inverse problem. So the forward problem is we have a material, we want to predict its properties. The inverse problem is we have some properties and we want to design a material based on those properties. So for polymers, we might have something like a high temperature dielectric that can withstand high temperatures being above 250 degrees Celsius. We need some sort of property goals, right? So in this case, maybe a temperature of 500 Kelvin that it can withstand. We use some proxy properties. So glass transition temperature might be a proxy for temperature resistance. Dielectric constant is related to energy density. So we want a high energy density, so it's a smaller capacitor. And then band gap, charge ejection barrier. These are kind of related to the ability of the material to withstand high electric fields. And then we use the genetic algorithm to actually design these materials. So for polymers, instead of having bears that mate and have children based on DNA, we have some blocks. And these blocks are taken from real life polymers. They're monomer actually. And then we break the polymer with chemically interesting substructures. And then we recombine these substructures. So in this instance, we have a polymer. We use something called bricks to break the polymer up into its interesting substructures. And then we see these stars are sort of joints, and we recombine the polymers at their joints, or the blocks at their joints. So we take some parent polymers, and in the crossover phase of a genetic algorithm, we would break them at one of these joints, and then we would recombine them with the different polymers at the joint that it was broken at. And then we might have some mutation that occurs. And after that mutation, that's when we'd integrate machine learning to predict the properties of the polymer. So that's for polymers. Now, if you were going to do something for a separate material like perovskites, you'd have to design your algorithm a little differently. But really the three main things you need if you want to use PolyGA or any genetic algorithm, you have to have some DNA or some sort of way to take the physical structure of your material and break it down into its base components. So for instance, if you're doing like a perovskite structure, that might be just elements. If you're doing a polymer, that's these chemically interesting fragments. So it would really be dependent on what you're trying to make. And then you need some sort of compilation algorithm that you'd have to write. And I'm going to go into how we do that for the polymers in a sec. And then you'd need some property predictors. So these are the machine learning property predictors. You'd also need some features or fingerprint of your material that you can rapidly create. So for polymers, the way we did that, I already said, right? We use bricks to break real polymers, and we take a bunch of real polymers and find their sort of DNA components, which are these chemically interesting fragments. And then we have a recompilation algorithm where we take a list and we have the order of each fragment always be the same, but we randomly decide which fragment to join at. So in this case here, we joined this fragment to this fragment, the leftmost fragment to the second leftmost fragment at the star blocks here. Let me just make sure you can see my laser pointer. Right, so this star we connected to this star down here, right there. And then in this other potential way of doing it, we connect this star to this star. So that's how we create these different polymers, even if they have the same chemical structures. So that's one way of doing it. That's how we do it. That's one way we do it. I mean, we have a couple different ways, but this is one way. And then we also have to make sure that they're actually realistic. So these polymers might not be realistic, and that's where you actually integrate other algorithms too. So not the genetic algorithm. After you design your hypothetical polymers or your hypothetical perovskites or something, then you might use like a retrosynthesis algorithm. This is a paper that one of my colleagues wrote on what that actually means, but I won't go into that too much, but just for your information. And then we take this new polymer and we look at its SMILE string. For a polymer, a SMILE string is just a string representation of its chemicals. But for something else, you might have a different, representation for perovskites, for instance. But we take this string representation, we fingerprint it with some fingerprinting algorithm that we write, and then we throw it through our machine learning models to predict their properties. So for this polymer here, we had predicted properties of 505 Kelvin, 5 EG band gap, and 4.6 is the dielectric constant. And so now that we have those three things, we would have some sort of fitness function we create. So for our polymer dielectrics, we might have these targets that I mentioned previously. And if they meet all these targets, we might call it a successful polymer that's met our goals. And then one fitness function we could use for this target is this clamping fitness function, where we take all of the polymers and for one generation, we predict their properties. If their properties above the target, for instance, if the predicted property of a polymer is 600 Kelvin, we might clamp it at 500 Kelvin. That way, once a polymer achieves one target, it focuses on achieving these other targets instead. If it was less than, we do a little bit different algorithm. And then we scale them all so that they're between 0 and 1. So that way, when we're weighting the glass transition temperature of one polymer, we don't weight it higher than the dielectric constant. So there's a bunch of different fitness functions you can use. This is one that I use a lot. But when we do that, I call it a clamping fitness function. With PolyGA, we have all of the averages for these polymers go above their target region. So the gray region that you see in each of these is sort of the target region for the polymer. The red region is this parent average. The blue region is this child average, and this will make sense as we walk through the algorithm in a sec. Average plus or minus the standard deviation for all the children, and then the parent max and min. So we see that all these averages start to go up really rapidly, or down, for instance, for the cohesive energy density. And so this tells us that we're starting to create materials that achieve all of our property goals. And again, the score we do, right, when we're assessing the fitness of a polymer to choose if it should be the parent for the next generation, again, it works just like the bears do, right? The parent's chosen based on how well it survives in that environment. We just use some sort of math to figure out that fitness score. In this case, it's just a linear combination of these min-max scale features. And this is just a UMAP. It's kind of like TSNE, where you project down the high dimensional fingerprint to 2 dimensions that showcases the chemical space of where our new polymers are. So these reference polymers are the polymers we use bricks on to break up the polymers. And then these other regions are these new polymers we've generated, the red region. And then this blue region is the successful polymers. So for this specific design case, we didn't, sometimes with genetic algorithms, you get lower diversity. So one way PolyGA tries to solve this problem is using migration. So you have, several islands, each one has a different fitness function. Maybe you maximize glass transition temperature, maximize band gap, maximize dielectric constant, and then do this clamping fitness function we talked about briefly. And then this is based on this paper by Verhelen, where we can have migration occurring between these islands so that as the glass transition temperature finds new chemical spaces that achieve really high glass transition temperatures, if they don't become parents of their specific island, they can migrate to the clamping island. And then after they migrate to that island, then we're able to integrate them with the parent population of that island to increase more genetic diversity in our children. So doing that, we can get way more chemical space being explored. So previously, I'll just go back quickly, right? It was just sort of this lower region down here. When we have this migration occurring, we get an entire circle of space explored. And that's because of these islands, right? So we have some regions that are high dielectric constant. We have other regions that are high band gap regions. And then we have some that are high glass transition temperature regions. So these are the regions of the chemical space that are most likely to achieve these targets. So a high glass transition temperature region. So that's what PolyGA is basically trying to do. So at this point, we'll run it. So what it does is crossover, it does mutation, it does mutation rate. You can select the DNA randomly, selection, which is based on the fitness function that you design. And you can also select based on however you want. And it's pip installable as well. So PolyGA is something that you can just use pip install to get. I also have a tutorial that's quite long on this GitHub page at the top right that you can run through. So I try to make it generalized. Again, it's for polymers. It would probably be easy to integrate it with small molecules as well. But I'm happy to work with other people as well if they want it or are interested in using it for other things. And then if you want to use the tool for this example, you would go to this link. I think they've been posted in the chat as well, and then press launch tool. For the tool, I am a fool and forgot to actually approve the newest version. So this older version still runs, but there's one tiny error in it that we will fix as we work through it. So I will run the older version, but if you watch a recording, the newer version should be up, and the newer version just fixed that one small error and added a little documentation. So
fantastic. Yes, thank you very much, Joe. So I'm going to ask a couple of quick questions, Joe, from the chat. Do you have an experimentally based criteria for combining the components? I believe, how do you decide the fragments, the chemical fragments that you're using as your building blocks? So
the way you decide it is you create your chemical fragments and then you combine them randomly with the with these blocks. So you start with a bunch of randomly generated polymers that have a block, and then you use an algorithm to recombine the polymers together. And then when you take that polymer, you split it, and then you randomly recombine it. So it's based on randomness. So if you wanted to do it not based on randomness, when you design your compilation algorithm, that's when you would actually specify specific design criteria that you want to like incorporate into your algorithm. So that's based on the application that you'd be using it for, I think.
Okay, cool. Thanks. Yeah. Another question is, what does chromosome mean with respect to polymer configuration? I think maybe it's a related question.
Chromosome, it just means that I tried to have it be fun. So it literally just means the DNA, right? So it's just a block, another way to name the block. I tried to make it more based on actual genetics just for fun.
Yeah, yeah. And a quick question right before we go to the tool. One final question. What are the parameters you're using in your charts where you show data clusters? So I believe, how did you do the 2D visualization of the data?
Yeah, so that's based on UMAP, which if you know what it is, it's uniform manifold approximation. I can't remember the exact term. But for those, you change the min distance and nearest neighbors and stuff like that. So when you do that, you kind of play. I mean, if you know what UMAP is, you maybe understand. If you want to ask about UMAP, I can give you the specific details. But if you mean something else, I can maybe clarify the question on that.
Okay. Yeah. Thank you, Joe. So at this point, I think we can get started with the tool. Hopefully everybody is able to open it and work along with it.
Cool. Okay, so I will start with explaining the tool. So the first thing I'm doing here is I use logging to actually to create messages for people. So in this first instance, I'm just describing the logging format for the messages that are going to be put in. And then Pickle is used to load the machine learning algorithms or machine learning models we use. I think a lot of people who do any sort of science stuff probably know what pandas and NumPy are. sklearn, this is the min-max scaler that I talked about earlier. So this is when you're designing your fitness functions. This is just for plotting. And then, of course, PolyGA is what we're actually going to be using here. So in this case, I'm importing something called PolyGA analysis. And then this will be something we use a little bit later. And then here's the actual stuff we're using when we want to run our algorithms. So RDKit is something that a lot of chemists use. So this is really for the polymer domain space. So if you were doing something with perovskites or something else, you might use a different type of function here. So these are just what we're importing. So we'll just run the import there. Now the fingerprinting, right? This example, by the way, it's not a real world example. It's just an example with some made up models I created. So I'm going to showcase a real world example after this, but it's the exact same run through for these. So in this case, for the fingerprinting, this is what I'm using RDKit for. I'm taking the smile string, and then I'm looking at the chemical based from RDKit and creating a molecule from that. And then I'm using this Morgan fingerprint. So a Morgan fingerprint is just a way to fingerprint your polymers. A fingerprint is, again, it's just that feature space you're using that you can quickly generate so that when you run it into your machine learning models, you can get a prediction of, it's quantifying the structure. So then when you run it through your machine learning model, you get some predictions out. And then I'm adding this fake fingerprint here, another fingerprint, which I'm just adding because I wanted to be able to make each fingerprint unique, right? So when you're generating new polymers, you want your fingerprint to be unique for your machine learning model. Okay, so again, this here is just an example. If you were to do this in real life, you design your own fingerprinting function, or you'd use an example like RDKit has here. And I'm passing the data frame, and I'm returning a data frame and then the fingerprint headers. So this way PolyGA knows what your fingerprinting headers are to run through your machine learning algorithms. So we'll run that. And then in the silly property prediction, again, right, this is where I'm loading these models. So I actually pass the models. So when we initialize the PolyGA planet, right, we'll pass the models to it. And then I'm passing the data frame and the fingerprint headers as well. So in this case, I'm loading the model, and then I'm predicting the values for each model. And we'll go into how this works later. And then I'm returning the data frame after I predict the values for all of the different properties. And the data frame, I'm just adding the properties on at the end and then returning it. So for these functions, these are things that you would define. And then after defining them, you could run PolyGA. So I'll go through that in a sec. And by the way, if this isn't making sense, I have a longer tutorial on the GitHub page that also walks through this in a lot more detail. Now, this is a fitness function. So this is the first fitness function we're going to design. So again, this is kind of how you want to design your properties. So we have the data frame and the fingerprint headers being passed. And we have these properties that we define below. So I already know what these properties are going to be. And I already know that these properties are associated with the names here. So this data frame key, this data frame key are these property names. So just to keep that in mind. So
Joe, can I just interrupt for a second?
Yeah.
To quickly answer something, there's an error that somebody gets, operational error, unable to open database file. Is this something?
We're going through that. Yeah. So we'll get to that down below. But I promise it's an easy fix. So I'll explain why you're getting that error.
Yeah. Just wanted to mention. Yeah. Go ahead. Go ahead.
So once so in this scenario, right, I'm just trying to make super cool polymers, right? I just made up some machine learning models that I made some fake data for, and I'm loading these models, and then I'm predicting the values, and I'm doing this scaling. So for each property, for each one of these properties, I'm taking the property values for all the polymers. I'm min-max scaling them to be between 0 and 1. And then after that, I'm doing this linear combination of these scaled values for each polymer. And then I'm adding that fitness score at the end. So in this instance, I'm trying to make all of these polymers super cool, super smart, super funny. But in a real world scenario, what I would be doing is trying to increase their glass transition temperature, increase their dielectric constant, etc. And so now we're going to get, so once we actually define these, so these are things that you would define, and then after you define them, now we would actually run PolyGA. So in this case, I have the model folder, which is in bin. I have the properties and their associated machine learning pickle files. And I'm making a dictionary where I store the property name, and then I store the loaded model. And of course, if you're going to do this, I use Poetry to manage my dependencies, but you want to use the same sklearn and pickle versions. And then here I'm defining a planet. So I'm making this polyplanet. I'm making the predict function, which is this silly property prediction, right? So that's where we define that up here. And I'm making the fingerprinting function, right, which we defined up at the top here. And then I'm loading in the models. So I'm passing the models to this planet, and I'm saving the folder in data. So I'm just making a new folder, saving it in data, and then the planet will be saved in this folder here. And then I'm making a land on this planet. So the idea here is we have a generative function. So this way, we can actually specify different generative functions for different lands. So we can make one planet that has the property prediction and the fingerprinting. We can make a bunch of different generative algorithms if you want to try to generate polymers in different ways or perovskites in different ways. And then we can pass different fitness functions as well. So maybe on one land, we want that super cool, funny polymer. On a different land, we just want to focus on having funny polymers. So then we would run that. And then in the nation, this is sort of where we define cultural bounds. So the selection scheme we want to do is elite. So we just always pick the best fitness scoring polymers. After selecting those parents, we want to compare their Tanimoto similarity scores, which is just trying to compare their genetic similarities so that we can try to pick parents that are chemically dissimilar from one another. And then the number of populations initial is the number of initial polymers we generate. But of course, you could also do a bunch of different other hyperparameters if you wanted. And you could load in your own initial population if you wanted. So we'll just run that. And now we advance time. So when this runs, it's going to start running through the algorithm. Okay. So it's going to do the age, right? It's just, some of these things are just kind of fun little things I added in just to make it more interesting as it runs. But you could also turn this off, right, with the logging function. So if we imported the logger at the beginning, but we could also turn it off if we wanted. I also added the ability to alter it, so you change this from polymers to perovskites or whatever you wanted. I just kind of, it's just supposed to be fun. I don't know. I don't get paid enough to not have fun, so. So we'll just wait for this to finish running. It should be pretty quick. So this is also why I did a silly example versus a real example because sometimes it can take a while to run. And now we want to plot it. So we're going to plot the lengths of these polymers, and we're going to plot their property averages over time. And one thing I'll add here, the data frame that's returned, this like settled nation, so there's certain keywords that each data frame has, and we can actually look at those in a second. So the settled nation is the land or the nation that the polymer is coming from. And then count number of successful polymers. So these are the polymers that achieve our goals. We just arbitrarily decided that our goals are going to be all of them are above 200 degrees or 200, whatever the units for this would be. And here's where the error is coming in from. So up here, like I said, we defined it in the folder data. So if we run this, it should give an error, right? And to fix that, we can just add a little data thing in front of it. So now it'll load the fingerprints and the data frame. And at this point, we can plot the average property, or the property averages. So when we defined how to plot the property averages, we looked at each nation, we looked at our properties and our goals, and we just said if the property is above its goal, we're going to color that in gray, right? Or if it's to be less than something, we color it gray. So that's all that did. In this case, we wanted all of them to be above 200. We see here that these two property values got above 200, but the polymer intelligence stagnated at 140. So in real life, you might have different sort of things. The other thing is, you actually in real life, you don't want your polymers to be getting too long, because the longer they are, the less realistic they're going to be. But because in our fitness function, we used the number of the length of the polymer. So some of these actually try to get longer because of the fitness function. So, in real life, you'd have some sort of algorithm you'd use to assess how accurate the generated polymers are, or the generated perovskites or something are. And here we're just counting how many actually achieve all property goals. None of them did. So because of that, we can run it again. So here, I'm just saying run 10 times. So run 10 generations of PolyGA. And so that's what it's doing here. And so in each generation, again, it's taking a polymer, it's looking at its fitness score, and then it's crossing it over with the other polymers that achieve the highest fitness. So that's what's happening in each run. So once this is done running, we'll load the data again. Again, here's another error, right? We just have to add data / or / planet silly.
So Joe, just a quick comment. If it's easy enough, can you put it in the chat where the error is and what you need to change it to? Like the data.
Absolutely. Absolutely. So the error is anytime you see this, let me go to the chat. So you need to add data.
Cool.
Right?
Yes, thank you.
So that's where the error is. Yeah.
Yeah.
So I'm sorry about that, guys.
For afterwards, we will have fixed it. So yeah, for right now,
okay.
Just
yep.
Yeah. It's maybe it's a good time to break for a couple of minutes. To answer one or two questions. I just wanted to quickly ask you. I saw something Tanya wrote in the chat, which I wanted to ask. So, are you using the SMILES format as the fingerprint here, and does it make a difference in implementing the genetic algorithm? What you use?
So we use the SMILES format to fingerprint it. So we have a specific fingerprinting function we use in our group. But I put in an example from RDKit, which is another fingerprinting function that you can use because our group one is kind of private. So this is what's happening. We take that SMILES format, which is the string, and then we convert it into a molecule, which is something that RDKit does for you. And then from RDKit, we put that molecule into this allchem.getMorgan fingerprint as bit vector. And this just returns a vector representation of your SMILE string in like a numerical representation based on the actual chemical, like the physical structure of the material. So if you were using something else like a perovskite, there's a different way that you would fingerprint a perovskite, right? So you could look at like what element is at each specific spot. That could be part of the fingerprint. You could look at the charge, like the ion charges for each element. So that could be part of your fingerprint. So your fingerprinting, the fingerprinting is really for your machine learning models. So what PolyGA does is it just takes a list, and that list is your list of chromosomes, and it looks at how you represent the chromosome. So it takes an ID and how you represent the chromosome, and that could be as SMILE strings. So in our group, we represent the chromosome as SMILE strings, but you might not do that for your research.
Yeah, got it. Thanks, Joe. Yeah, why don't you continue with the notebook? Yeah.
Sure. So we ran the algorithm longer. That's what we were doing here. And then we just wanted to load it again, and we want to compare how it did. So you see, we're plotting this on a log scale. So these are the first 10 generations, and these are the next 10 generations. So you see, it's still going up for the intelligence. It's sort of stagnating for funniness and coolness because it's trying to increase intelligence more, but it's getting kind of stuck here. So one thing we can do if we're trying to increase the intelligence more for PolyGA is we can define a new fingerprinting function here. And in this fingerprinting function, all we're trying to do is maximize intelligence. We don't care about anything else. And we create a new land and a new nation. And in this land, our fitness function is now just make the smartest polymer. So before, if we scroll up to the top here, the fitness function was make coolest, funniest, smartest polymer, so which we defined up there. So now going back down here and loading that and advancing time again. So now it's doing it for both the original nation that we created and then this new nation we called Eureka. And so you'll see that Eureka is now only age 1, right? So it's a new land that's just been colonized on your imaginary planet, whereas Awesome Land is age 20. So I saved the date or the age of the land and the age of your nations. I don't know, it just adds more fun. Makes it a little more interesting to watch. And then it's going to run through both of these. Now what's happening here is you're having migration occur. So my default, the migration rate for this country is 0.02. So 2% of the polymers from this nation, Eureka, will migrate to Smartland. The default level or will migrate to the United Polymers of Cool. So the default rate is 10% or 1%. And then the emigration selection is best worst. So what's happening here is the best polymers that didn't get chosen as parents will be the ones to emigrate. So that way we can try to increase the intelligence of the United Polymers of Cool people a little more. The one thing here, you can change a lot of these things, and there's different emigration schemes you can do. So that's all in the documentation for PolyGA. But again, I'm kind of hoping that you can use PolyGA, and I try to make it generalizable. But I'm also hoping that you can kind of learn how to make your own genetic algorithms if you want to. PolyGA, it's a lot of nice stuff, but you don't have to use it. So again, we're going to add data at the front here, right? Because I neglected to be responsible enough to approve the newest version, sorry. And then we'll plot the property averages again. So it's loading all the data, and it loads it in one data frame. So, but you can parse the data frame. In fact, maybe I'll show you what the data frame looks like in a second. So one thing you'll notice here is Eureka, our little land here, it happened to have an increase in coolness and funniness, but that's probably because migration is occurring to planet Eureka, or to nation Eureka as well from here. So these have been going up over each generation. This is 10 generations, but we see that the intelligence is really what's going up the most. So that's at 160, whereas here it's only at 150. So it's prioritizing increasing intelligence. And then we see for these ends here, these 10 generations is the generations that there's been migration from the nation of Eureka. And we see that there was a quick jump in intelligence at that first nation, or at that first generation. And then it sort of slowly increased. We'll see there's a decrease here, right? Because now funniness, it's not being prioritized because of the clamping fitness function. And we're getting these super smart but not very funny polymers, as you see here, coming from Eureka to migrate to the United Polymers pool. And then we can plot the average lengths again, plot the successful polymers, and then complete the run. So if we wanted to keep running this, we could run it indefinitely, or we could remake it and have a different fitness function, or we could change the fitness functions around if we wanted to. This just closes your SQL connection to the database. So the one thing here, you'll say, well, how come we didn't get an intelligence above 200? And this is the key point, is these are all based on your machine learning models. So all the genetic algorithm stuff you run is going to be dependent on that. So if you don't have any polymers that have an intelligence of 200, then you're never going to have a polymer that reaches that goal, right? Because it doesn't exist. So it turns out we can't achieve this goal of 200. So you got to keep your goals realistic when you're using the genetic algorithm. So this is the silly test. I'm just going to show you a real example that I ran through. Again, it runs much slower, so that's why I didn't. But this is where I defined my fingerprinting function and my DNA. I have a larger DNA list that I use, and then my machine learning algorithm loading and how I actually combine the smile strings. So again, I define my predicting function, define my clamping fitness function. This time I care about glass transition temperature, band gap, dielectric constant. I made a nation, that uses these things. I ran through it. So I'm going kind of quick here because I know we have limited time, but you'll see the exact same idea, right? So here it's real values, dielectric constant. Here is going up. We're trying to get above 4. We're trying to get above 5. We're trying to get above 500 and below 80 here. So we're seeing that it's going up pretty quickly with each generation. For these 3 ones, it's going down quickly here, which we like. The lengths are pretty stable, right? For polymers, we don't want them to get too long. So, 4 blocks is usually ideal. And we're just running through each time, multiple generations. So, after 10 more generations, it achieved its goal here. It's getting close to achieving its goal with band gap and dielectric constant and glass transition temperature. But glass transition temperature stagnating, right? So we ran one with a new nation that we tried to maximize glass transition temperature. So again, it's the same exact concept that I just ran through with all of you here. And we see the second nation has a high glass transition temperature pretty quickly above the goal. And we see that it's been increasing the glass transition temperature in this area here as well. So yeah, I just wanted to run through that quick so you guys see that it's not just made up, but this is how we actually design hypothetical polymers. And if you read the paper I referenced at the beginning of this talk, I also talk about it a little bit. And here we see that we found 68 polymers that achieved our goal from Clamperton and 32 from TG10. So yeah, these are the names of the nations I gave just for fun. So yeah, that's my TED Talk. So I hope it was somewhat helpful. I guess I'll open it up to questions now.
So we can go ahead and answer some of the questions. Maybe the first thing is somebody did point out that even after adding the data slash, they get key error, none of planetary ID are in the columns. And any idea about that?
So did you make sure you ran through each of these here? So maybe try re-adding the data slashes and then clicking the arrow at the top and restarting the kernel and running all cells. So if you do that, it should hopefully run. I'm guessing you just missed one of these cells.
Yeah, that's probably what it is. We do have a number of questions, so this is good. We can go through these questions now. Let me read them out to you from the beginning. Okay.
Sorry. Before you start that, one thing I want to say is, because I don't want you to overwrite your data, you can't remake a new planet with the same name. So at the end here, I just run this cell here, which deletes the planet. and then try restarting and writing the cells. So just add this little line here at the end and run it, and then do that. Okay, so after I will add this to the chat. And now, yeah, open for questions.
Yeah. One question is, do the different islands have the same number of individuals in each generation?
No, so they can. So you can define all that if you want. So what you would define is for each nation, how many parents you want for each generation, right? So you could have it where only 2 parents mate, or you could have it where you have 10 parents and they all cross over together. So you can kind of define it, but by default they do. Now, the one thing where they won't is sometimes in RD kit, you'll have a molecule that gets made that's not real, or that it can't be actually made or created, or it can't be fingerprinted because it's unrealistic, in which case it throws an error. So then we would skip it. So then you'd have some failures. So you would have fewer children than you would expect.
Okay, good. Thanks. Yeah, here is another interesting question. How do you select how to break a polymer into fragments? I could imagine some polymers would not have natural fragments to break into.
Yeah, that's a good point. So if you type in bricks, so I think I can even show it here. And if we type chemistry, this is the algorithm we use from RD kit to actually break up the chemical fragments. So there's a paper on this that you can read if you're interested. But this is how we find the fragments for our specific case. So for instance, if you had polyethylene, right, that's probably not going to have, it'll have 1 fragment, and that'll just be the monomer.
That's right. Yeah. So a related question that I had to that, the fragments reminds me. So you mentioned this can be adapted to perovskites or other materials. So can we directly take what you have and just supply fragments of perovskites and a predictive framework, and it will work for that?
Yeah, I mean, the way that I implemented this is all of the chromosomes are added in a list. And so if you know the order, if you were doing perovskites, for instance, we could adapt it. We could work together and try to adapt it to work for perovskites. It's kind of hard for me to think of the example explicitly, but the way it works for us is we have a list, and then we randomly cross over the list. For perovskites, you might also have a list, and you might also be able to cross it over and still have it work out. So you could use it for other things as well. The base thing here is just when you define how you actually put the polymers together, which if you go to the documentation, you can actually read how we do that. And you can see an example of how we put the polymers together. You could put it up together with the perovskite in a list format and extract the specific ions that are supposed to go in each cell from that. So you might be able to do it with this.
Yeah, thanks. Any quick comment on any measures for the model's uncertainty for the generated candidates?
Absolutely. So our models actually do output the uncertainty. So when you make your fitness function, or when you make your property prediction here, you can actually say that you also, and in fact, we do this, we save the uncertainty as well when we add it here. So instead of just adding the prediction like we do here, we'd also do the uncertainty. And then you could integrate that with your fitness function here, where you say you only want the most certain polymers or something like that. So you can do that.
Awesome. Yeah. Here is a slightly different question, which is, has your group or others tried to synthesize your predicted polymers? What are the results of that? Any
Yeah, so we actually have several generative algorithms we use. One being the genetic algorithm. We have another person who uses PolyG2G. So if you Google that, you can look that up, which is what Rishi works on. So for all of these, the biggest thing is that retrosynthesis algorithm. So you make a bunch of these polymers, and a lot of them aren't synthesizable. And then you run through some sort of retrosynthesis algorithm to predict which ones are most likely to be synthesizable. And then you take those ones, and again, it might only be like 20 over 10,000 polymers or something, just because of the nature of how these things work. And then you would send those to chemists who would try to synthesize them. So we're actively working on that right now. But we do have a general idea about which ones are more synthesizable than others.
Yeah, great. Question by Brett Henderson. Very cool work. Is there a reason why you don't include polymer length in your fitness function, or is it something you may want to constrain?
So I've experimented with this. In my paper, I talk about this. You can constrain the length. So you can make polymers that are only 4. So when I do the splitting, there's a hyperparameter you can add where you can either just split in the middle, so all polymers are only 4 blocks in length, or you can let it grow naturally. And that growth kind of depends on the mutation rate you choose for your children. And if you constrain it at the maximum, so you say it can't be bigger than 6 blocks, for instance, you can absolutely do that. And I've done that. I found that what works better is trying to figure out what mutation rate corresponds to like a stable length. Because you don't want to constrain the minimum, because sometimes these 2-block polymers are very easy. I mean, they're much more likely to be synthesizable. So if you say you can only be 4, then that's not good. But you can constrain the max length. You could absolutely add that in the fitness function if you wanted to. And I've done that, and it does work sometimes. Yeah, it does make more realistic polymers.
Awesome. Yeah, very good. Here are some questions by Bakhtiyor Rasulev. What about copolymers? How would you encode those?
Yeah,
and what level of structure is used? Yeah,
that's a great question. So we do not just linear polymers. We also do, I can't think of the word right now. I'm just totally blanking. But for copolymers, we haven't integrated that yet, but I absolutely could see a way where you create 2 polymers and then you run like a fitness function and a fitness function, where you create 2 polymers and then you look at their copolymer configuration and then you see how that property value is. So you could easily, I think, expand this to do copolymers too. In fact, one of the people, but the thing is you need models for copolymers. So one of the people in our group is working on models. His name's Shivank for copolymers and blends. But really that's constrained by the copolymers. I think the genetic algorithm aspect of that wouldn't be too hard to implement though.
Yeah. Maybe you were talking about branched polymers. I don't know if
it was branched polymers. Thank you for, yeah.
So, there is a comment, a question by Tanya in the chat. Like, if it's basically the same thing, if you use a branched polymer instead of a linear polymer, like, do you need it to be linear, or, can it be extended?
So it can be extended. So when you make the polymer in the compilation algorithm, which I load here, in fact, I could actually go to the PolyGA page and go through the algorithm quickly, but you can define it so that you can also do these other types of polymers. So it doesn't just have to be, so this is actually the algorithm we use, right? So in here, we just combine linear polymers, but these stars, you could also make it so you could add branches and stuff. And you could extend it for that, for sure.
Great. Yeah. Thanks. Yeah. Okay. In the next 2-3 minutes, let's answer a couple more questions, and then we can end this for today and take everything else to the ML group forum. So for now, okay, here is a question by Juan Carlos. When you do recrossing for the polymer example, how do you guarantee valid polymers are generated from their parents using SMILES?
So yeah, that's a great question. So there's a couple ways we've tried to do that, where we look at bonds that are unrealistic. And after creating the children, we rescreen the children based on those bonds. And then if they're an unrealistic bond, we would just throw that child out. So that's one thing we've tried. We've tried doing it where we look at the retrosynthesis after the fact. That's a little slower algorithm, so we can't run it during. but then we just screen all the polymers after they're generated. And I think that's actually the best way to do it, where instead of trying to make something realistic, you just let it run, and then you screen for realistic polymers after the fact. So again, you can definitely look at the bonds to see which ones are more or less realistic.
Right. So it's going to be too complicated to include the realistic nature of it as part of the fitness function, I guess.
It's not too complicated. So you can absolutely include it. It's just about time. So if it takes, for instance, the retrosynthesis algorithm can run for like 100 seconds for just one polymer. So then it's not worth it, right? Because the whole point of the GA is to be a little faster, and it doesn't dramatically improve the results. So in the interest of time, it's nice to just screen everything after the fact. But you could incorporate it into the retrosynthesis algorithms then.
Yeah.
And the reason it's nice to do it after the fact is because if you do a run and it only takes like 2 hours to run and make 16,000 polymers, and then you see that it hasn't achieved the property goals, right? You don't get any polymers that achieve those goals. Then you know that you should do a rerun where you change it a little bit. Whereas if you screen it during, then you're spending an extra like 100 seconds per 16,000 polymers trying to see if they're chemically valid, and then none of them actually achieve the property goals anyway. So it's just kind of a waste of your time. But you could incorporate it if it's fast.
Yeah. Thanks. Yeah, very good point. Okay, so I'm going to ask like a general question as like one of the let's do this as the final question. A general couple of questions for your thoughts. So this is based on a question from Daiki Ikeuchi. When is a GA particularly useful? For example, the number of features, design variables is high or low, and when the number of experiments, how many experiments are possible, etc. So that's one question. Your general comments on when a GA is applicable, how good it is. And I wanted to add another thing to it, which is are there other techniques for inverse design that you recommend or you try instead of GA? These are the final questions. Let's say.
Okay. So for polymers, there's also variational autoencoders, which have been used. And then there's the graph-to-graph translation, where you take a polymer and then you try to just change that polymer into a slightly different polymer that achieves your property targets. So the GA is nice because you have these predefined blocks and you have these machine learning algorithms, and you quickly design the target criteria with your current models and then try to design polymers that achieve those target criteria. Whereas something like an inverse design algorithm like the PolyG2G, you have to train a model that has those criteria already defined. So if I want to change my glass transition temperature to 500 Kelvin to 600 Kelvin, I have to retrain the model to actually do that completely. For PolyGA, I just changed the fitness function a little bit. So the way that the GAs are nice, in terms of experimental design, it's about exploring a really large space. So polymers there's like infinitely many polymers. And each one, you can do also forward design, where you take these blocks and you just combine them in every single way possible. And then you run machine learning algorithms over every single one of them. And that would create like millions of polymers that you could screen. So the GA is nice because it's a lot faster to find these target criteria versus doing it that way. But that's another valid way if you have the computer resources.
Okay. Yeah. Thank you very much, Joe. Fantastic.